Right. Welcome, everybody. I hope you can hear us out there. Welcome to today's talk given by Andrea Albano from Università del Salento in Italy. He'll talk about set-theoretic solutions of the Yang-Baxter equation and their reflections. Please.
Yeah. Okay. So good afternoon or good morning, everybody. First of all, thanks to the organizers for letting me be here and present the talk. So what I would like to do today is to give a basic overview on the context in which I'm working in as a PhD student in the University of Salento. I will try to give a basic overview on the set-theoretic Yang-Baxter equation and on their reflections, with just some final remarks on some results that we have obtained together with Marzia Mazzotta, the University of Salento, and my PhD supervisor, Paolo Stefanelli. So let's start from the start. The Yang-Baxter equation is basically one of the most fundamental equations in mathematical physics, and today is at the heart of quantum group theory. Its roots can be found in the investigations of Yang and Baxter, who were working in statistical mechanics, in particular with two-dimensional quantum integrated systems. Formally, given a vector space V and a linear endomorphism of the tensor square of V, then we say that R is a solution to the quantum Yang-Baxter equation if it satisfies the equation on screen. Now, of course, studying the solutions of this equation in their entirety is a hard task, as you might expect. So one thing that we could try to do is to determine a simpler class of solutions. So before doing that, let me just point out that if you want to have a mental picture of the Yang-Baxter equation, you can imagine a dynamical system, a two-dimensional dynamical system with three particles, for example, in motion. One dimension is spatial, one dimension is time. And what the R matrix, what the R map tells you is how they behave after a collision in pair. The Yang-Baxter equation itself is just telling you that the way in which the pairwise collisions happen is not important, basically. So
explain what there's little r, presumably it's big R.
Yeah, I'm sorry. The ID is the identity. So basically, R tensor ID is just I'm sorry for that. It's just a typo. This is the first typo. I'm sorry. So R tensor ID and the other maps similarly. Yeah, sorry for the typo. There's also a small r there. It should be a big R, of course, capital R.
Is the
yeah, exactly. So you can there are actually linear maps acting on a threefold tensor product of V, where R tensor identity is just apply R on the first two coordinates and so on, and similarly. So here, just because I am here, okay, now let me just point out that I'm kind of lying to you because this is not exactly the Yang-Baxter equation. It is called the braid equation or the braid identity. They are equivalent after a simple change of coordinates, basically. So the class I'm pointing to is the class that was determined by Drinfeld in 1990. What he suggested is to interpret the braid identity in this case in the category of sets, study the solutions of this equation in this setting, and then apply a linearization process to these solutions to have full-fledged quantum solutions. Now, in this talk, I will only mention set. Sorry?
Could you go back to the previous slide?
Yeah, of course.
Tell me, this R times it is a map from d squared times d squared to itself?
No, it's a map from the R times id is the map from d cube to d cube. So basically, as before.
The cube, okay. So two coordinates for R and one for it.
Yeah. I should
For
have,
it too. Oh, yes, sorry.
exactly. I should have been more detailed on that. Sorry. Yeah, so basically this is just the same idea where you take a threefold Cartesian product now of D with itself, and you let R act on the first two or the last two coordinates. It's simple as that.
Yes.
Okay, thank you. Now, for the remaining of this talk, I will only stick to set-theoretic solutions. So anytime you will hear from me saying a solution, I will only mean a set-theoretic one. Now, the real, in some sense, advantage of pertaining to set-theoretic solutions is that we have coordinates. There are actually different notations that we can, types of notation that we can employ in this setting. The one I will be using mostly in this talk is this. So if you take a map R from, recall it is defined from d squared to d squared, then you can project the map onto its coordinates, coordinates, and thus introduce two families of maps. They are just set-theoretic maps, they're just functions, lambda A's and rho B's, and so write your solution in this way. It makes sense, I will try to explain it in a while, to define a solution left non-degenerate if all the lambda maps are bijective, dually right non-degenerate if all the rho maps are bijective, non-degenerate if it is both left and right non-degenerate. So in this way, you have coordinates. You can take your braid identity and write it into coordinates. It's just a boring game, and if you do that, you would obtain a system of three nonlinear equations in the coordinates x, y, z. So basically, solving the set-theoretic Yang-Baxter equation amounts to solving this system of equations, which is, of course, in its entire generality, difficult. I mean, there's no direct way to employ any tool in a direct way, indeed. So let me make some examples. The easiest one that you can think of is called the twist map or the trivial solution on a given set. Its action is just given by flipping the coordinates. A kind of generalized example of this is given by the class of the so-called Lyubashenko solutions, where you take two functions, two maps, Fg, they must commute. They are defined from D to D, and you write your solution in this way. It is an example, it is quite straightforward to understand when the solution is left or right non-degenerate or even bijective. Okay, so an entire class of important solutions is given once you do this thing. If you assume that the lambda maps are all the identity and write your second coordinates, the rho maps, in infix notation, so introducing this binary operation, for now it's just that, it's just a magma on D, a magma operation on D, it's quite straightforward to understand when it is a solution. As you may already know, this is a known identity. It is usually called the left distributive condition because the operation here is required to self-distribute over itself on the left. So dr in this way is a solution if and only if the operation is self-distributed on the left. As I said before, this is a known structure. Formally, in general, if you have a set D together with a binary operation that defines this condition, then you have a so-called shelf structure. Now, let me just point out that the condition I'm using here is simply equivalent to the fact that the left multiplication operators, that is those maps Lx that send y to x triangle y, they are endomorphism of the structure. This is equivalent to the condition I'm showing you. So it is indeed useful to add conditions to this structure. If you have a shelf, then you can have a rack when all left multiplication operators are bijective too. So they are automorphisms of the structure. In particular, a quandle is a rack when x squared equals x is an identity of your structure. That is when it is idempotent. Okay, these structures were already known in the works of Joyce and Matveev, who were interested in knot theory, even though there were previous mathematicians, for example, John Conway is one of these, who were already working with these type of structures. So I will try to give only some examples, the easiest ones, I think. One of the most important is called the conjugation quandle. It is defined on a group G, where the binary operation is simply the right conjugation operation. So you just like forget the operation of the group in some way, in some sense. A similar but different example is called the chord quandle, where you again take a group G and define a triangle operation in this way. It is interesting also because of the fact that it is an example of an involutory quandle, in the sense that each left multiplication operator is an involution of the structure, is not only a multiplication. Now, of course, not all racks are quandles, and it is straightforward to, okay, it's not that straightforward. It is not difficult to have an example of a rack, G triangle, again defined through the help of a group G, without an importance, unless the element that you fix to define the operation is in the center of the group. Okay. So we have determined an entire class of solutions, a simple class of solutions, and each solution pertaining to this class is is named to be of left-derived type. Of course, here I'm sticking with the left picture, but we can imagine a dual version of it where we can get right-derived solutions with defined through the help of right shelves or bundles or racks. But if you have noticed the left-right symmetry of the Yang-Baxter equation, it is indeed possible to prove that these two pictures, left and right, are equivalent in some precise sense. So this class of left-right solutions are quite interesting in that they are some properties of them, most properties of them, can be described in terms of the shelf or rack or quandle that defines the solution. For example, it is bijective. It is straightforward to understand when it is bijective or involutive. Here, as an involutive solution, I just mean that its square, so R squared, is the identity on D squared. Now, this is a behavior that we would like to have for general solutions. Of course, we don't know if it's possible at this point, because not every solution simply is of this type. So we might want to understand when and whether there is a structure for a given solution, which may be general as you want, that helps you in this way. One thing to notice here, two things to notice here are these. These types of solutions are left non-degenerate simply because all the lambda maps are the identity. And the shelf structure is, let's say, a witness to involutivity, in the sense that the solution is involutive if and only if the shelf structure is trivial. That is, in better terms, it is the projection quandle on D. So X triangle Y is always Y.
Do you mean here that whenever you have a bijective solution, it comes from a rack?
No, I'm not saying yet.
Under this
no.
assumption that you start with a solution from a shelf.
Yeah, exactly. Exactly. So the types of solution that you see here of left-derived type. So it is indeed interesting to understand whether and when we can have a structure that behave in this way for the solution. One way to do this is quite pictorial, let's say. So I would like to describe it to you. If you consider a braid diagram of this form, which is a simple one, where you have two strands, the left one crossing over the right one, you can interpret the action of the set-theoretic solution as in this way. if you start from two colors from the top nodes or labels, as you may want, you can take your solution, apply it at every braiding that you can see. Here we have two braidings, and use the colors on the top to deterministically determine all the other colors. Of course, which nodes I'm referencing to the nodes that you have on the two strands after each braid. So here in this picture, we have 6 nodes to color. Now, the thing is that if you assume that your solution is left non-degenerate, then you can play the same game starting with a different set of colors, starting from a coloring of the top left 2 nodes in this way. For example, let's just say they are Y and X. Indeed, recall that left non-degeneracy amounts to the fact that all the lambda maps are bijective. In this way, you can determine all the other colors. For example, the one on the top right is indeed lambda y inverse of X. Now, what I think of a mathematical miracle, let's say, is that if you take the expression defining the last color, then you can prove that you have a binary operation, a seemingly difficult binary operation that defines a shelf structure on your set D. Not only that, all the lambda maps that you have for your original solution are automorphisms of the shelf, of this shelf structure itself. Again, you have a shelf structure that you defined through a solution that you started with, so you can associate to it a second solution determined by this shelf structure, as I was showing you before. This new solution, R prime, is called the derived solution, the left derived solution of your original one. And this is indeed only possible whenever this solution is left non-degenerate or dually right non-degenerate. Remember that there is this duality. Okay, so this is not just a game I'm playing because there is an important property that connects the two. Indeed, if you start from a left non-degenerate solution and define your left derived one, they are conjugate. They are conjugate as maps from this squared to this squared, where the bijection F, capital F, that ensures the conjugation is as simple as that. So basically, what you get is that every property that is invariant under this notion of isomorphism is indeed determined by the shelf structure associated with the original solution. In general, given two solutions, we have an example. We will say that they are Drinfeld isomorphic if they are conjugate. For example, in this way, this is just an example. Okay. Now, the thing is that this was indeed what we were looking for, because notions as bijectivity, involutivity, or other things are indeed determined by the left derived solution that you can construct. If your original solution is bijective, you can compute its order employing this connection. But of course, not all the properties that you may want to study of solutions are of this type, in that not all properties are invariant under this notion of Drinfeld isomorphism. So what we might want is a
These functions, rho and lambda, they come with D, or
they come with the map. They come with the solution. Yeah, they're just the projections of the solution on the two components. And when you work with it, it is actually apparent why it is so advantageous to work with set-theoretic, with these set-theoretic notions. Simply because you have coordinates, you can do this thing. While in general, for general quantum solutions, it is not clear if you could do that. This is one of the real advantages, as simple as that.
the derived solution will be non-degenerate as well.
It will be left non-degenerate, of course. It might be right non-degenerate, depending on the shelf. If the triangle operation, I'm saying.
And lambda rho it will inherit or from the first solution.
Yeah, for the derived solution, you have, of course.
Same lambdas.
No, you don't have the same lambdas or the same rho maps, because for the derived solution, as you said, as you can see here, the lambda maps are all the identity. All of them are the identity map, while the rho maps are given in this way. For example, rho yx for the derived solution is y triangular x. Yeah. So they are not the same. We have two pairs of families.
And you apply the process again?
Yeah, you can.
Back or you get
You can compute the left derived solution of a left derived solution. And the interesting thing is that what you get is the same left derived solution again. So basically, the rule that applies the left derived construction applicable to every left non-degenerate solution is idempotent.
Okay.
Is idempotent, yeah. And this is indeed a very interesting example, a very interesting property. And yeah, thank you for that. So yeah, even though we have that, there are some notions which are not invariant under this notion of isomorphism. So we might want to have a weaker notion of, a stronger notion of isomorphism, where we assume our map, F, capital F, to be split as F little f times F. Formally, given two solutions, DRES, we say that a map from F, from D to E, is a set-theoretic morphism. It is not a common name, it's just a name I'm using here for the sake of it, just to give it. So a map F from D to E is a set-theoretic morphism if it satisfies this equation on screen, which is analogous to the one before. So F times F is a conjugation, it conjugates these two solutions, but now is of a particular form, So in a sense, you can think of F as respecting the lambda maps and the rho maps of your solution. Okay. So in this case, we have a category whose objects are all solutions, whose morphisms are all set-theoretic morphisms between solutions. The class of all non-degenerate solutions form a full subcategory in this case. Recall that a non-degenerate solution is a solution in which all the lambda maps and all the rho maps are bijective. Okay, so we are asking a non-degeneracy on both sides in this case. Okay, so this is one stronger notion of isomorphism, and there are indeed many properties of solutions that are invariant under this new notion of isomorphism. To study these properties, there one structure in particular has risen that can describe in quite an interesting way these properties. I will try to give a description of this structure and briefly explain why it is important in this matter. So what I'm talking about is a structure known as a skew brace. A skew brace is just a pair of two groups on the same set. Here the operations are denoted as plus and circle. Plus is not assumed to be commutative. And these operations have to satisfy the equation that you see on screen. This might be a far-fetched structure at first point, but there are indeed very important examples of this. For example, radical rings are one important class of skew braces, one in which the plus operation is commutative. a radical ring here is just a non-unital ring, which is which coincides with its Jacobson radical. It's just that. Regular subgroups of the holomorph of the additive group are another important example. It's not just an example. I will just say that. So skew braces are what have been obtained in a long process that started from some observations due to Wolfgang Rump in 2007, and have seen many mathematicians working on it. I'm not citing all of them for time limits, for time permissions. This definition of skew brace is due to Leandro Guarnieri and Leandro Vendramin in 2017. Now, the important thing about skew braces is that if you start from a skew brace, D plus circle, remember plus and circle are the two group operations, then you can define a bijective non-degenerate solution in this way. It seems to have a difficult structure for some sense, but it becomes easier once it is studied more. And it is indeed in trying to understand this type of solutions that many mathematicians have spent much time in investigating this. Here, I'm just citing some of them. Of course, for space and time limits, I cannot do all of them. One thing I would like to point out is that you can actually play with the skew brace structure, trying to see if you can weaken the assumptions that you're making here. One example of that is the work of Catino, Palazzo, and Stefanelli, where they have weakened the hypothesis on the additive group. Okay, yeah.
So the solution was the superscript minus?
Of course, the superscript minus here is just the inverse with respect to the circle operation. While here with minus simply, I'm denoting the inverse with the respect to the additive operation. Yeah. Of course, what's really important here is not only the form of the structure, but its relationship with the entire class of non-degenerate solutions. Indeed, what makes skew braces this strange structure really important is this fact. From a skew brace, we can define a solution, a bijective non-degenerate solution, and we can do this in a functorial way, where the morphisms are just those morphisms as before that have to respect the two group operations. It's not only that. It's not only that. So here is one component from a skew brace induces a solution on the same set that we are working on. It's not only that. This functorial procedure that produces solution is a component of an adjunction that is a component of an adjunction between the two categories that I've talked about at this point, that of non-degenerate solutions and that of skew braces. Here, I just want to point out that the way in which you go back, in a certain sense, that is from a non-degenerate solution back to a skew brace, is by using what is known as the structure group of the solution, which is indeed an important structure that has applications in other areas and is interesting to study for reasons apart of the Yang-Baxter equations. And so this adjunction is really what we were looking for in a certain sense before, because in this way we can translate properties, set-theoretical properties of solutions in terms of skew braces. Of course, there are advantages and disadvantages. I just want to point out one of them, one disadvantage, and one disadvantage that one may encounter is the fact that the unit of this adjunction is not necessarily a monomorphism. So in this sense, a solution is not necessarily immersed in its skew brace structure, which is this structure that is defined on this group. Okay, so these are two notions, the shelf associated with a solution and the skew brace associated with a solution, with a non-degenerate solution, that allow you to study the properties of your solution depending on which notion of sameness of isomorphism you may want to use. We can have a general framework with which to work that tries to put things together in a sort of sense. Yeah.
How does structure group define the skew brace?
It's not really straightforward. It's not really straightforward. Basically, you have an action, a left action from this group to another group. And what you have is a bijective one cocycle between them that permits you to define a new group operation. That it's not really straightforward. Of course, I'm leaving here these citations to leave the possibility to understand this. And of course, I'm open to any questions. So thank you. As I was saying, we can have this discourse in a under a general framework. The general framework is given once you recall that starting from a left non-degenerate solution, then the lambda maps are automorphisms of the structure. In a recent paper by Dr. Ribolevich and Stefanelli, they have introduced the notion of twist, which is nothing more than a formalization of what I was saying before. A twist is just a map lambda from D to the automorphism group of the triangle that satisfies the equation that you see on screen. As strange as it might seem, this is just the first braid identity I was showing you before in terms of the lambda map and the triangle operation, where the raw map is just this thing, is just this. So in this way, what we can prove is this. If we start from a shelf and have a map lambda from D to the automorphism group of the triangle, where triangle again is the operation on the shelf, then the map that you see on screen is a left non-degenerate solution, if and only if the mappa lambda is a twist as before. That is, it satisfies the equation that you see on screen, which is basically amounts to say that if you want to solve the set-theoretic Yang-Baxter equation, then you might want to fix a shelf and determine all its twists in this sense. It is all these maps lambda that satisfies the equation before. Notice again that whenever we have a twist lambda of this form, then the left derived solution of this solution is determined by the shelf operation that we started. That is, if you try to construct the shelf structure associated to a solution of this form, then you just come back to the original shelf that you were considering. For example, if you take a skew brace solution, then, and if you take a skew brace solution and you try to write it in these terms, so in terms of twists, what you get is that its associated shelf is the conjugation quandle of the additive group. Okay. So now, of course, we have this description of solutions which basically amounts to trying to understand these self-distributive structures called shelves, trying to understand these maps, lambda, that are twists. And of course, we might want to try and understand how we can not only derive solutions to the set-theoretic Yang-Baxter equation this way, we may also want to try and understand how we can apply this framework to connected areas, to connected teams to the Yang-Baxter equation. One of that is the area given by the so-called reflection equation. So if you recall before, the picture I was trying to give you, where you have a dynamical system with, let's say, 3 particles interacting with them, you might wonder what happens when you add a boundary to the system. For example, when the system is monodimensional, is spatially monodimensional, and there is a boundary on one side, you may wonder what happens when the particles collide with each other and interact with the boundary. The equation, one equation that in this setting tries to formalize the idea that the order of the order in which the collisions happen between them, between particles and between the border is not important. So to formalize this idea, it is important, it's interesting to study the so-called reflection. Here, I'm just showing you the set theoretical version of the reflection equation, again, which is defined in this way. dr is a solution, so each reflection is associated with a solution. K is simply a map, a function from D to D, which we will call a reflection, and they have to satisfy this equation, where again, R is simply working on D squared, on the Cartesian product of D with itself, and id K times K is simply the Cartesian product of the identity and the K map. So it works on D squared. It goes from D squared to D squared. The first instances, the first investigations of these maps can be found, of this equation, can be found in the works of Cherednik and Skyrin, who were interested in a particular setting in which you have solitons interacting with themselves and with the boundary.
Here, kappa is the interaction with the boundary.
Exactly. And here, as before, R formalizes the idea of having a collision between particles, and K formalizes the idea of having a border. So in this sense, writing id times K is simply saying that you have the border only on one side, in this case on the right side. And the equation in particular is saying to you that the order in which two particles collide with themselves and with the boundary is not important. For example, it is a system when you have particles of the same type, for example.
What's the significance of having R 15 times kappa twice?
Because you first have a collision between two particles, then a collision with the boundary, and again, collision with two particles and the collision with the boundary. Here, the collision with the boundary that you see happens for the two particles. So we have two particles interacting twice, one each, with the boundary. And in this way, the order in which this phenomenon is happening is not important. So we are formalizing this idea.
And would it be similar to just have it once, or ID times kappa is equal to ID times kappa?
This is indeed an interesting question, to which I cannot answer right now. I think not, because this picture is just a simplification. This equation actually comes from a formal description of the physical system that you have. So I don't know if there are systems in which you have a similar phenomenon happening. It might be interesting to understand if and when it happens. So here we are just focused on two collisions with the battery. Okay. Yeah.
The physical system, you said it's just one dimension.
Oh, one dimensional, yeah. It's two-dimensional in the sense that it's spatially one-dimensional and temporally. Yeah.
And the particles move on the line.
Yeah.
And if they collide, then they reflect, or what's the idea?
Depending on the physical system it's a bit complex than that. For example, you have these solitons. Of course, I'm not an expert in this area. For example, you have these the systems in which where you have solitons, where the collisions might be a bit complex than that.
They may have more complex interactions.
Yeah.
So it's like little waves that oscillate with the phase, and then when they pass each other, when they interact, the phase shifts.
Exactly.
So they collide, but the internal states are
Exactly. Exactly. So there are internal degrees of freedom that we don't see here, and that are whose behavior before and after the collision is described or governed by this K map here, by this reflection, and by the R map, by the R matrix. Okay. So in this remaining time, I want to describe to you how can we apply the tools before in this context. I will try to be brief. Again, notation. Let me give names to things. If dr is a solution, then we say that the set of all the reflections of the solution is kdr. Again, let me note that a reflection that is a K map here satisfying this equation is a reflection to a solution. So the study of reflections goes along with the study of a fixed solution. Okay, so when your reflection is bijective, then we put it in the bin K bij. For now, they are just sets. It is actually interesting to understand whether there is a notion of composition, but it is not actually clear. Of course, are they empty or not? So am I describing to you the empty set? Of course not. For example, given one simple solution, for example, in this case, the Lyubashenko solution, then you can actually see and determine all solutions in this case. In general, for a fixed generic solution, then the identity map is a reflection in this case. So we are not talking about empty sets in this case. Okay. So let me just give a very quick overview on different approaches that have been used so far. Indeed, this is a quite recent area of research, that of set-theoretic reflections, I want to point. For example, Cauderlier, Crampé, and Zhang in 2013 employed a folding method to determine new solutions to the reflection equation. And speaking of skew braces, de Commet in 2019 introduced a particular notion of skew brace action to determine new solutions to the reflection equation, to the set-theoretic reflection equation. I won't try to be to give details in that. One of the first general methods came from Smoknovich, Vendremin, and Weston in 2020, applying the notion of braces. Here, a brace is a skew brace with additive group commutative, with abelian additive group. Doiku and Smoknovich in 2021 investigated the relationship between the reflection equation, set-theoretic Yang-Baxter equation, and quantum integrable systems in general. It's quite interesting. In 2022, so very recently, one paper from Lebed and Benjamin introduced this generalized notion of derived solution using a reflection coming from a fixed solution. Moreover, they were one among the first focusing on involutive solutions. So focusing on reflections to involutive solutions. Now, the reflection equation can be rendered a bit more complex, let's say, adding parameters that I'm not showing you right now. One type of this investigation on the set-theoretic parameter reflection equation is given in a paper by Doiku, Mazzotta, and Stefanelli. Very recently, Lin Coterlier, 2025, this year, studied Poissonian symplectic properties of set-theoretic reflection equations. And again, recently, Davide Ferri, using the work of Descommets on skew braces, introduced the notion of group reflection for braided group. Here, braided group, you might want to read that as a skew brace. So he introduced this notion of group reflection and studied how to lift reflections from a solution to the structure group. So in basically giving important information on the study of reflections on skew braces. Now, in the work of Lebed and Benjamin, it was noticeable that there are two important classes that we may consider. In general, given a set, D and the map, sigma, that I'm simply writing in this way, you may think of sigma either as lambda or as rho, as lambda map or as a rho map. Then we say that a map K from D to D is called sigma centralizing or sigma invariant, depending on which type of condition it satisfies. For example, sigma centralizing means that it just commutes with the action of the sigma. Rho invariance simply means that its action on the subscript of sigma is not important. So what is possible to prove is that for an involutive left non-degenerate solution, K, a lambda centralizing map, is automatically a reflection for the solution itself. In a dual, let's say dual version, if R is an involutive right non-degenerate solution and K is a Rho invariant map, then it is automatically a reflection. So we have these two classes of reflections, the lambda centralizing at the Rho invariant, that can be important depending on the non-degeneracy condition that you apply to your solution. Now, what we wanted to try among other things is to get rid of the involutivity condition. The solution, recall, is involutive whenever its associated shelf is trivial, being it left or right, again, depending on the non-degeneracy assumption that you're making. So if we want to understand reflections for non-involutive, non-necessarily involutive solutions, then we should take back the study of reflections to the study of the associated shelf of the solution. This is indeed possible. And recall, here I'm just recalling you that the shelf structure in this is defined in this way. This is indeed possible. And indeed, what we could prove, among other things, is that if you start from a left non-degenerate solution, dr, without any assumption on involutivity or even bijectivity, and take K, a lambda centralizing map, then it being a reflection can be completely cast in terms of the shelf structure. So this lambda centralizing map K is a reflection if and only if it satisfies this weird system. Notice here that because of this reason, this is equivalent to say that K is a reflection for the associated left-derived solution. So lambda centralizing reflections can be studied just looking at the left-derived solution. This is possible, of course, for left non-degenerate solution. In the case your solution is bijective, non-degenerate, so you add the condition of right non-degeneracy, then the system is becomes simpler in a way. And in this case, a lambda centralizing map K becomes a reflection if and only if it is a particular endomorphism of the shelf structure. Of course, notice that here involutivity is witnessed by the triviality of the shelf structure again. Of course, there can be a dual version for only right non-degenerate solutions. Here, I'm just denoting for the sake of information how you can define the right shelf structure for right non-degenerate solutions. But the situation is quite different because differently from what happens to the Yang-Baxter equation, where you have a left-right symmetry. For the reflection equation, you don't have that, simply because you have one boundary on one side. So we should not expect a symmetry happening here. Indeed, for right non-degenerate solutions, then K, a map K, which is rho invariant, is a reflection, if and only if it commutes with all right multiplication operators in this way. So in this way, is this kind of simpler to study solutions in this setting for right non-degenerate solutions. Of course, we have a same conclusion as before. Now, the fact that, and I'm finishing, the fact that the study of reflections for left or either for left or right homogeneous solutions can be casted in terms of its shelf structure is quite important. And for us, is a justification to study different structures associated with shelves, fractal quantums. Let me just point out one last thing. If you have a rack, here rack, I recall, is a shelf where each left multiplication operator is bijective. Then you can define an interesting group, which is called the left multiplication group. And it is simply defined as that group generated by left multiplication operators. It can be proven that it is a normal subgroup of the automorphism group of the rack itself. And our justification to our ulterior justification to study these type of structures is that for a left-derived solution coming from a rack, then you can quite easier, you can understand reflections in an easier way. For example, and these are just applications of the last two results. If you take all those maps, K, that are endomorphisms of the structure of the rack, and that in addition centralizes all the left multiplication operators, then you have for free reflections for the associated solution. If you just stick with bijective reflections, then you have indeed inequality. So it is indeed important. This is just another motivation to study these types of structures. Just to give some open problems and some possibility of research here. What our findings suggest, of course, there are way other motivations to do this. ours is just another motivation to do that. So one interesting thing to do is fixing a class of racks F. You may be interested to study the orthomorphism group and the left multiplication group of the rack itself. For us, it determined reflections to the associated solution. Of course, there are some works in this context, but at this point, it is not really complete in some sense. I will only leave some references here. So this is one first thing that one might want to do. The second thing is, okay, is there really any other reflection which is not lambda centralizing or rho invariant? The answer is, of course, yes. There are examples, there are important examples, which do not follow in these classes. But the question is, can we relax the condition on lambda centralizing, on being lambda centralizing and rho invariant to get new reflections? This is indeed a second way of research, which might be interesting to do. So this was the last thing, and thank you for your attention.